Fusion energy aims to bring the power of the sun to planet Earth. One of the projects to achieve this aim is IFMIF EVEDA. The goal of the IFMIF EVEDA project is to produce an engineering design for a fusion neutron source so we can test different materials to be used in fusion reactors. These materials must be able to sustain an extremely intense bombardment of neutrons inside a fusion reactor without getting damaged. Do these materials exist? How do we test them? Finding answers to these questions will be a vital step in enabling future generations to see a fusion reactor in operation. A team of European and Japanese experts was formed to take up this challenge. On February 5, 2007, the IFMIF EVEDA project started under the Broader Approach Agreement, signed between Euratom and the Japanese government. The goal is to create prototypes of the main facilities of the IFMIF neutron source and to finalize its design. The IFMIF neutron source will replicate the bombardment of neutrons that is expected to hit the wall inside a fusion reactor. To generate a shower of neutrons, a high-intensity deuteron beam is accelerated. The beam hits a lithium target at the end of the accelerator line, which in turn generates a neutron shower that jets towards the volume behind the lithium target. This space is used for material testing.
High-energy neutron emission is generated inside fusion reactors. So we will have to conduct a range of tests on materials to identify those that can withstand the flux of neutrons in future fusion reactor called DEMO. This is why we would like to build the IFMIF fusion neutron source. Here in Japan, at Rokkasho Fusion Institute, we are building the most challenging part of the accelerator for the fusion neutron source. I believe the research we have embarked on may well have many benefits for future generations.
The project faced many challenges to achieve the milestone of its first phase. The Europe-Japan team has been working closely to overcome many difficulties. What has been achieved by this team? Let's take a journey through the past 13 years to see its achievements. The IFMIF EVEDA project consists of 4 activities: engineering design activity, test facility, lithium target facility, and accelerator facility, Lipac. Let's start with the engineering design activity. This played an important part in the design of the facility. In June 2013, we published the IFMIF Intermediate Engineering Design Report. Secondly, the test facility will test different fusion reactor materials in a bombardment of neutrons. Test modules were manufactured to validate their design, with the ability to test over 1,000 material specimens. Tested materials need to be protected from overheating. For this, a full-scale cooling system prototype was successfully built and validated in Karlsruhe, Germany. Thirdly, the lithium target facility consists of a liquid lithium loop and lithium target. The target is where an intense source of neutrons is generated by the impact of accelerated particles into the fast-flowing lithium. The design for this started in 2009, and its construction was completed in 2010 in Owarai, Japan. By March 2015, the world's largest liquid lithium loop had been successfully built and tested. In 2017, studies about lithium loop erosion, corrosion, and remote handling systems were successfully completed in Brasimone, Italy. We now come to the accelerator facility, the low-energy part of the IFMIF fusion neutron source accelerator, but also its most challenging part. The prototype accelerator, called Lipac, aims to generate a deuteron beam with a pioneering current of 125 mA in continuous wave. Building Lipac, one of the most powerful linear accelerators in the world, is a great challenge and requires a strong Europe-Japan collaboration. The design and manufacture of the accelerator system to be assembled in Rokkasho started in 2007. In 2009, the headquarters building was completed, and the project team started to coordinate the preparation.
Initially, the design and manufacturing of the accelerator components was shared by Europe and Japan with a close communication about the interfaces and using a 3D computer model. Also, we had an intensive collaboration, including the participation to the acceptance test before delivering the components to Rokkasho. Finally, we could start the joint work as a team for integrating the components to a prototype accelerator according to the planned sequence.
The accelerator is built in phases, adding accelerator parts step by step. The first part of the accelerator, the injector, was delivered to the site by Europe in March 2013. 7 years after the design process commenced, the first proton beam was extracted in November 2014. It was the first major success of the Lipac integrated project team. The fruitful collaboration between Europe and Japan is growing stronger.
So working in a Japanese-European environment is very challenging because of all the cultural differences and different languages. But when you overcome a problem as a one team, it's much more rewarding.
The next accelerator part to be installed was the RF quadrupole, also called RFQ. With a length of 9.8 meters, this RFQ is the longest in the world. The RFQ and beam transport line are assembled in the accelerator with laser precision. Positioning tolerance is within 10 micrometers. A celebration was organized with important delegations from Europe and Japan. For the RFQ to accelerate the beam at full capacity, hundreds of kilowatts of RF power are required. The commissioning of the RF power systems was completed, and in October 2017, the accelerator up to the medium energy transport line was ready to operate. The injection of the first beam required a lot of patience and joint effort from the Europe-Japan team to handle this complex and powerful machine. As a result, the first milestone to accelerate a beam of protons was reached. In March 2019, the preparation for the more challenging acceleration of deuterons was initiated. The most important achievement up to now. 125 mA beam of deuterons was accelerated successfully, up to 5 megaelectron volts, a breakthrough for accelerators of this kind.
So many components of Lipac were made in Europe and nothing similar in the world. So its installation here in Japan is really a big challenge. But I always felt the strong enthusiasm of the European colleagues coming here, and we wish to realize that. So we share the same goal. So this created a very strong joint team.
The successful acceleration of a beam of deuterons marked a significant project milestone, validating the concept of the low and medium energy accelerator parts. In March 2020, a joint declaration of Japan and Europe was signed for continuing this fruitful collaboration. The next Lipac objectives are to validate the design in continuous beam operation, including the high-energy part with the superconducting accelerating section. Thanks to remote working, both here and from Europe, and other special measures, Lipac's activities were able to continue in spite of the COVID outbreak in 2020. In parallel with the first project successes, additional engineering design activities have started on the future neutron source to be developed in Japan and Europe. PAR celebrations represent the success of this amazing collaboration and the team spirit of our project. The achievements of our project were possible through deep collaboration between Europe and Japan based on mutual trust and understanding. The IFMIF EVEDA team continues to explore new challenges of fusion engineering. We are confident there is more to come.